All right, everyone. If you thought last week's ANOVA was exciting, you're going to love this. So this is two-way between subjects ANOVA. So when do you use two-way between subjects ANOVA? Well, it's when you have two independent variables. So you've got two between subjects independent variables, specifically is the one I'm going to show you here. So each one of those has to be a variable, so it has to have at least two categories for each, right? So a 2 by 2 would be the simplest. And you've got 1 dV that's measured on an interval or ratio scale. So it's ANOVA when you've got more than one independent variable. This is a simple way to think of it. And the reason I teach it to you is because you go in there thinking you're going to do ANOVA, one IV, and next thing you know, your chair or your committee like adds on another one. You're like, what do I do? This is what you do. You do two-way between subjects ANOVA. So for example, let's say you wanted to look at the effects of therapy and sex on treating depression. So you've got IVA, which is therapy type, and let's say for this example, it's therapy and no therapy, and you randomly assign. IV2 is sex. You've got male and female, and that's quasi-experimental. Your DV is level of depression, and let's say it's operationally defined in this study as BDI or Beck Depression Inventory scores. Higher score, more depressed. So here's what you end up having. You've got, so here you've got row is sex, male and female. The columns are therapy, therapy and no therapy. And you have what's called crossing of conditions. You've got males who receive therapy, males who receive no therapy. Females who receive therapy, females who receive no therapy. So we call this a 2 by 2 because the first IV has two levels, the second IV has two levels. So if you literally multiply them, like 2 times 2, you end up with 4 groups. So note that 2 IVs result in 4 different total groups. We call that crossing. So does it appear that the effects of therapy for treating depression were the same for males and females in this hypothetical study? So there's your data right there. You've got your lines. The solid line is males. The dotted line is females. The left set of dots is those who got therapy. The right set of dots are those who did not get therapy. And note that the lines cross. So it looks like therapy improved depression for the females, so their lower scores are definitely lower. That first bottom left-hand dot is much lower under therapy than under no therapy for females. But what's going on for males? Well, they're actually more depressed under therapy and less depressed under no therapy, right? So when the lines cross like this, it's a clear indication of something called an interaction. That is, the effects of one independent variable are different for the levels of the other independent variable. And that's what we call an interaction. We're going to talk a little bit more about that. So therapy appears to have worsened depression for males. They actually had higher scores than under control of no therapy, right? So let's try another example. And this is the example we're actually going to analyze in when I go through one of these with you. So we wanted to look, for example, at the effects of sex and bully victimization on a child, as a child, good Lord. Sex and whether you were bullied or not as a child, on whether you differ in your hostility as an adult. So males and females, and whether they were bullied or not, is the way it's defined in this study, whether it results in, hostile adults, right? And whether those effects differ for men and women. So the hypothesis for this was again someone's dissertation. Does being bullied as a child have a different effect on males and females' levels of hostility in adulthood? This particular hypothesis is set up, well, we'll note a couple things. The DV is hostility in adulthood, but the hypothesis talks about both independent variables. You see that it's got bullied as a child, or not, I guess, is implied, and males and females is the levels of sex. So the hypothesis here is asking, are the effects of being bullied different for males and females in terms of their adult hostility? So this is what we call an interaction hypothesis. You're hypothesizing, or this is not specific. It's not like one-tailed. They're just saying, hey, are the effects the same of being bullied or not for men and women? So it's an interaction hypothesis. So first IB is sex, male, female. Second one's bully, victimization, and the way this person defined it was you're either bullied or not. So, like, they answered some questionnaire, and if they're bullied, you know, emotionally or physically, whatever, they just said, yep, bullied. Otherwise, you were not bullied. And the DV was level of hostility, the usual psych scale, 1 to 20, higher is more hostility. So in this particular study, again, it was a real person's dissertation. They had 178 participants, and they were asked if they were bullied in school when they were a kid, and were assigned to one of 4 conditions based on their responses. And the full thing is a quasi experiment, right? We're not randomly assigning them to get bullied. We're not randomly assigning them to their sex. So there are 4 cells, again, in a 2x2 analysis. They are not bullied males, not bullied females, bullied males, bullied females. So one way you could think of doing this sort of study is to do a bunch of independent samples t-tests, right? You got a 2-level bullied or not, you got a 2-level sex. Why not just do 2 t-tests and call it a day, right? It's lame for the following reasons. I love how honest these slides are sometimes. So first of all, most importantly, you're probably most interested in the combined effect. You want to know, are the effects of sex and being bullied, or being bullied different for the different sexes? And independent t-tests wouldn't let you do it. You could look at, males and females combined. Do they differ in their adult hostility? People who are bullied or not, do they differ in their hostility? It looks at only one independent variable at a time if you do independent T's. 2A between subjects ANOVA allows you to look at that simultaneous effect of both independent variables at the same time, so it's cool. So then the usual one, I always bring up is when you do a bunch of tests on the same DV, you end up with type 1 error inflation, right? You got that family-wise alpha level again that accumulates. So you want to use 2A between subjects ANOVA. Specifically, this is a 2x2 factorial ANOVA is what we call it, which simultaneously, look how excited I am, which simultaneously evaluates all possible levels of the IVs, including their combined effect. Wow, I was excited when I wrote that. So, but it's true. So you get to simultaneously look at the effect of both independent variables rather than one at a time, which is kind of, not as fun. So the assumptions of 2A between subjects ANOVA aren't that bad. Independence, you guys have heard this enough. It's a between subjects design. That's what it means. Normality, you've heard this enough too. The scores in each level. Combination of levels of the independent variables are approximately normally distributed. Great. And I tell you how you test it. 3, this isn't shocking either, right? Homogeneity variance, basically the spread of scores is the same for the DV for each combination of independent variable levels, right? So males who are bullied, females who are bullied, males who are not bullied, females who are not bullied, all those have the same, they're about approximately normally distributed, and their scores are all have about the same variance or spread. So I just tell you how you test it. There is no backup test. It's not robust to violations like usual from this, so your only hope is to use a tighter alpha level. So maybe use 0.01 instead of 0.05, okay? All right, so the effects are a little different here because, well, let's just talk about them. So with 2 IVs, there's actually 3 effects in the ANOVA. So back in the day, you just had the 1 IV effect and then error, and then you got the total, right? Well, now we got 2 IVs, so it turns out there's 3 effects plus the error plus the total, okay? So what are they? You get something called main effects, and main effects are the effect of an individual IV pretending the other one isn't even in the study. So it's basically like doing a one-way ANOVA. So you get the equivalent of a one-way ANOVA or an independent T if it's only 2 levels for each IV separately. So you get one of the effect of sex. It's going to compare the average adult hostility of males versus females. So it ignores the fact that bullying is even in here as a variable. But then you get your own test that's bullying or not. So it's all people bullied versus all people not bullied, compares their hostility, and it ignores the fact that there's males and females. So these are the effects of single independent variables at one time. This doesn't answer the question of, are the effects of being bullied different for men and women? Okay. You get this third thing called the interaction. And that's really what's cool about two-way ANOVA. It's the combined effect of both independent variable A and independent variable B. It's the test of whether the effects of one variable, independent variable, are the same or different across the levels of the other variable. Call that an interaction. So this is the means in APA format, of course. And so try to find the means. There's lots of means now, is what's basically going to happen here. Find the means for each of these effects. So the effect of sex, for example, would be at the bottom there. 9.15 is the average adult hostility for all males. It would be compared to 8.67, the average hostility for all females. That's what's tested by the main effect of sex, number 1 above. It just compares those. It ignores the fact that people were bullied or not. So it's kind of like a one-way ANOVA or independent t-test. How about the effects of bullying? Where are those at? Well, that ignores the fact that there's males and females and just combines them all. Bullied people, not bullied people. So it's the ones that are here on the row, 8.27 and 9.45. So it'll tell you if bullied people differ from not bullied people, ignoring the fact that there's different sexes, okay? So it is the effect of one independent variable at a time. So how about this interaction effect? Well, remember it's a 2 by 2, and it literally 2, like times sign 2, you end up with 4 different cells. So there's 4 means. That's how you figure that out. They're here. You got males who are not bullied, females who are not bullied, males who are bullied, females who are bullied, right? You see those 4 means? And then, of course, they each have their own standard deviation as well. Lots and lots and lots of means going on here. So thinking about the sources of variability, this pie chart is all the variability in adult hostility among the participants in the study. There are some differences that can be accounted for in adult hostility, accounted for by sex. So it's like the eta squared for sex, or the omega squared for sex. So that little black chunk of the pie, for example, may be variability in why people are hostile as adults. That is for whatever reason, you can predict it by knowing their sex. Then there are differences that are due to being bullied or not as a child on adult hostility. And that would be the little stripy part there. So that is differences that you can account for in adults' levels of hostility that, if they're bullied or not, you can predict it, that little tiny chunk. And then finally, you've got the interacting effect of A and B, that is sex and bullied status or whatever as a child, which is the checkered part there. And that is variability that's not predicted just by sex, not predicted just by bullying. It's the two things combined predict that variability. So that is the third effect in your between subjects two-way ANOVA. So all the gray is stuff that you can't predict. That's just unknown. We don't know why people are hostile. They're just hostile, but we know these little tiny slices can predict due to their sex. Some of it's due to having been bullied as a kid, and some of it is the interaction of those two things together. So these things are the eta squareds that you calculate. So when we calculate those eta squareds and I ask you to interpret them, it's basically what slice of the pie is predicted by that independent variable main effect or the interaction. So a little bit more on main effects. Again, it is the effect of one IV on the DV without taking into account that the other IV even exists. So it is like you did a one-way ANOVA. So for example, what effect does being bullied have on hostility in adulthood without taking sex into consideration? So you pretend sex doesn't even exist in the study. This is essentially the same thing as doing the two independent samples t-test, one for each IV, right? So in this example, you might hypothesize that people who are bullied would be more hostile than people who are not, right? That makes sense. You would also have a hypothesis about sex, possibly. So if your main effects, so if your independent variable has more than 2 levels, you do have to do Tukey tests, just like with one-way ANOVA, to follow up your main effects that are significant. So in this one, they only have 2 levels. You're either bully or not, you're either male or female, and so we don't have to do Tukey tests, basically, is what this slide is telling you. You just look at the means, or if you're me, you look at the plot to see who's higher. If it's significant, you know they differed, just look at the 2 means, and I'll go through an example of that. But if you do have 3 or more levels, you would use Tukey, just like we did with one-way ANOVA. It'll break down those main effects and tell you exactly which groups differ from exactly which other groups. Your interaction is when the effect of one IV is different at the levels of the other IV. That makes the most sense to me, saying it that way. There's lots of ways to say that, but it's basically, you know, that the effect of the IV isn't the same for all levels of the other IV. It differs. That is an interaction. They interact. Do you think it's possible that being bullied results in higher hostility than not being bullied just for males? But maybe there's no difference for women, or the opposite effect. Getting bullied makes them less hostile. Like, who knows, okay? Those would be interaction effects, where the effects of being bullied are different across the levels of the other independent variable. That is, the effects of getting bullied were different for men and women. So what we're saying here is that the effects of being bullied are dependent upon sex, right? If you think through it, that's what we're saying. So being bullied doesn't affect hostility for females in this example, but it facilitates hostility for males compared to those who are not bullied. So interactions, the easy way again to see is you plot the means and you see if the lines cross. That's how you can tell if you have an interaction easily. So this is an interaction plot of those means for the interaction. And what do you see? Well, the lines cross, don't they? If the lines cross, you've got an interaction effect, or probably there's, if it's statistically significant anyway. We got that, always got that problem. But if the lines cross, you probably have an interaction. If you had enough power, you'd definitely find an interaction. So that's what this says. When the lines cross, you've got an interaction effect. That means the effects of one independent variable differed at the levels of the other. So what's going on? Among those who are not bullied, looks like that's not a big difference between their hostility levels on the left there, right? The 2 dots or the diamond and the square are kind of close to each other. But among those who are bullied, the 2 on the right side of the plot, you can see it looks like bullied males were more hostile than women, right? So that's what appears to be going on. So this is new. When you have a significant interaction, you have to do something called simple effects tests. So just like when you had a significant one-way ANOVA and your IV had 3 or more levels, you had to follow up with Tukey post-hoc tests. Or if it was repeated measures, you had to do a bunch of t-tests. Remember that from last semester? Here you have a couple steps. First step is, okay, interaction significant, I got to follow it up with simple effects tests. And this is the new thing for this week, I think, besides interaction. So if you find the ANOVA indicates a significant interaction, all you know is that the effect of the one IV is different at the levels of the other IV. That's all you know. So this kind of wording should start to sound familiar after a while. It's an omnibus test, right? You just know, okay, there's some sort of interaction here. What is it? So you don't know exactly where those differences lie. So you must do something called simple effects tests, and they're similar, again, to how you have to do multiple comparison tests for one-way ANOVA. I'm going to teach you how to do it. If the interaction is not significant, you just stop. You don't have to do these tests, okay? So you only do them if the ANOVA is significant. So the way I teach it to you, I have you do the simple effects tests anyway. That way, you don't have to run the SPSS twice, basically is why I do that. But normally, or what you would do is you would ignore the simple effects test if the interaction was not statistically significant. That's what you do. And they're obtained through something called SPSS syntax. You don't just click a box. We actually got to type a little bit of code here. So this is what's new. So because these simple effects tests typically have, well, there's more than one, we want to do a Bonferroni corrected alpha level on them. Just like with the post hoc tests that we were doing at the end of last semester, we want to do a Bonferroni corrected alpha level to account for the fact that we're doing multiple tests on the same DV, and it will inflate our type 1 error. So, you divide it by the number of tests you're doing. 0.05 by the number of tests you're doing becomes your new alpha level. And I'll show you an example of that. And there's the basic Bonferroni formula. 0.05 divided by the number of simple effects tests you're doing. So, it turns out there's two different ways to do simple effects tests. One's called between lines, one's called across the lines. And you pick the one that's most interesting for you or seems to answer your study hypothesis the best. So when I was taught to do this, we just did them both ways, always. And that's not how I'm teaching you guys to do it. So here's that plot again of those four means. Let's say the interaction was significant. We want to know, okay, what are those interaction effects? How did the effects of being bullied differ for males and females? So one way to do it is compare levels of A within levels of B. So we're holding B constant and comparing the levels of A. So this would be, for example, we hold bullied constant and we compare males and females. So we compare A, sex, within B1, which is not bullied. That's one of the two simple effects tests across lines. The other one is there. For bullied people, everyone's bullied, we're going to compare the males and females and see how they differ. So that is two simple effects tests. The red one comparing those two means, which is basically a t-test, right? And the blue one comparing those two means, and we're going to evaluate each one with a corrected Bonferroni alpha level of 0.025, 0.05 divided by 2. And that is one way of looking at your doing your simple effects to figure out what's going on with your interaction. You compare across the lines. Well, the other way to do it is instead of holding bully victimization status constant, meaning hold it constant, compare the two means, hold the other level constant, compare the two means, you could go along the lines. That would be comparing levels of B within each level of A. So we're going to hold sex constant. For males, we're going to compare those who are bullied or not and see whether they're more hostile when they're not bullied or bullied. Similarly, there's a second test for females, right? We're going to compare among females the average hostility of those who are bullied or not. That is the second type of simple effects test. So the first one is between lines, right? It goes across the lines, I guess. This one is along the lines. So which one do you do? The one that best answers your hypothesis or makes the most sense. There we go. Which is what I say here. So sometimes you have to follow those up with simple multiple comparisons on the simple effects tests, because those are basically t-tests. But if you got 3 or more levels, you've got 2 separate one-way ANOVAs. That's what those boil down to, and you got to do Tukey tests. Because in this study there's only 2 levels. If it's significant, just look at the means, which one's higher, but look at the picture, which one's higher, which one's lower. But if you have 3 or more levels, you would need to actually go ahead and do follow-up tests, just like they were one-way ANOVAs, and that would be Tukey. All right, and remember to use your corrected Bonferroni alpha level when you're evaluating your simple effects tests. So, so if the simple effects test is not significant, the IVs involved in that simple effects test do not significantly differ from each other on the DV. So you wouldn't do multiple comparison tests, you just stop. So you only keep going, it's kind of like the gate. You only keep going, moving through gates if they're unlocked. And unlocked means SIG's less than your alpha level. So there's a couple different decision rules now, because we've got multiple different effects going on here. For your main effects and your interaction, it's the usual one. If SIG's less than 0.05, reject the null. Okay, the groups differ on the DV, whatever groups are being compared. So for a main effect, that means the main effect groups differ. If it's the interaction, it means the effects of one IV differ at the levels of the other. If your SIG's greater than 0.05, those groups don't differ. Okay, there's no significant difference between them, whatever means are being compared, or no interaction. So for the simple effects test that we'll do, it's slightly different because we have a alpha Bonferroni, right? So you need SIG to be less than alpha corrected Bonferroni, for you to reject the null. And again, if it's less than your your Bonferroni corrected alpha level, it means the groups differ. There's significant difference between those means. It's greater than 0.05, no difference. So it is basically, it's the same rules. Hopefully this starts to make sense to you guys. So it's the same rule, compare sig to alpha. Just here the only difference is you got to remember to use alpha Bonferroni for the simple effects tests. So if you had the effects of B is what you were interested within each level of A, that would be 2 simple effects tests. You would use alpha Bonferroni of 0.05 divided by 2 or 0.025. How about measures of effect size? Eta squared. So not but squared, we're at n squared this time. But it's the same thing it always means, right? It's proportion of variability. It's that slice of that pie that is accounted for by that main effect or the interaction. That's what it is. Higher proportion, higher, more important effect that it is. Hopefully you pick that up in meta-analysis. So here's the formula. It's the sum of squares for the IB, whether it's IB1 or IB2, divided by sum of squares total. So that's not different. The sum of squares for the, or the eta squared for the interaction is the sum of squares for the interaction divided by the sum of squares total. So it's actually the same as it was before if you really think through it. We just divide the sum of squares for that thingy by the total. But we do have to hand calculate the total. So for your simple effects, it's also the same thing. Sum of squares for that simple effect divided by the sum of square total. The thing that's weird is you got to get the sum of squares total from the prior table. It's not like the sum of squares total for the simple effect is from the prior table. So for all, the sum of squares total equals the following. Sum of squares for the main effect of IB1, sum of squares for the main effect of IB2, plus the sum of squares of the interaction, plus the sum of squares error. You add those things up in the table and then calculate your eta squareds. And yeah, here I'm just telling you the totals on the output. I mean, sometimes they equal what you need on SPSS's output or corrected totals. Sometimes they don't. So my advice to you is just sum them. Just bust out the calculator function of your phone and add them up, and you'll always be right instead of guessing. So I suggest you calculate by hand the total sum of squares and total degrees of freedom. Your AP format, nothing fancy here. F with your degrees of freedom in parentheses equal to your actual F value to 2 decimals. P less than or greater than either alpha or your alpha Bonferroni. And then you throw your eta squared in there to 2 decimal points. And again, everything but eta squared comes right from your output. So we don't hand calculate much in here. We mostly just add and divide. So you ready? You guys ready to do this? I'm excited. Let's go ahead and calculate a two-way between subjects ANOVA. We're going to look at that person's dissertation that was on the effects of being your sex and being bullied as a child on your adult hostility levels. It's a very psychologist sort of one because I used to teach at a psych school. So does having been bullied as a child have a different effect on males and females' levels of hostility in adulthood? So this is, they're not saying males will be more hostile or females will be more hostile. This is kind of like a two-tailed hypothesis, right? They're just saying, do the effects of being bullied or not differ for males and females? That's basically what this says. So we've got sex, again, male and female, bully victimization, 2 levels. You're either not bullied or you were bullied as a child, one of those 2 things. And your level of hostility on a 1 to 20 scale, higher score, more hostile. Here's what the variables look like in the file. You've got 1 column for each independent variable, sex and bullied status, and you know that underlying those words, there's numbers. It's like 1 and 2 or 0 and 1, something like that. And the final column is their DV. It is their hostility scores. Here's the means. So again, tons and tons of means come out of this. They're all in the descriptors table. And there's just, note that N differs. You see that, the far right column? It differs for each group. So the power that you have actually varies across the different effects in a two-way between subjects ANOVA unless you get exactly equal sample sizes for each combination of IV levels. In this case, they did not. So there's our means and our standard deviations. What do we need that for? Table 1. There's always table 1 in APA. That's what you need them for. So first thing you get on your output is the test of a homogeneity of variances assumption. Familiar with this? It's Levine. Use the based on mean row. So this has got to be old hat at this point. Have we? Is the assumption met? If that thing's greater than 0.05, that sig value for based on mean, we have met the assumption. It is, so yeah, we met the assumption. There's our rule. So we've met the assumption. We have basically equal variances. We didn't, so we don't have to do any accommodation for that. We just keep going. So the variances are relatively equal. And I just tell you, if it was significant, you got a problem. And what do? You could possibly use a tighter alpha level, maybe 0.01 for the ANOVA effects, something like that. Basically, write me an email if this happens to you. So question 1, again, there's 3 effects. Main effect of each IV, and then the interactions. Let's go through them one by one. Is there a main effect of sex on hostility? That is there a difference between males and females adult levels of hostility regardless of bullying? Okay. So lots and lots of crap in this table, so I crossed some stuff out to try to make it easier for you. You got a row for sex, that's one IV. You got a row for bullied status, that's the other IV. And then you got this one that's sex star bullied status. That is the interaction effect. And then you have error. If you add up all those sums of squares, that gets you the correct total. Don't use total. Don't use corrected total. I mean, look at them. They're like 17,003. They're just, they sometimes work. Sometimes they don't. Just add it up. Just ignore total and corrected total and make your own. So anyway, where is the main effect of sex? It's the row that just says sex. So the sig value for that is 0.5. Is 0.5 less than 0.05? No, not even close, right? So there is no main effect of sex. What does that mean? That means men and women were equally hostile as adults. That's what it means. The average hostility level for males and females did not significantly differ. So, and again, this ignores whether they're bullied or not. Okay, this is just males versus females. That's all it is. It's a main effect. So how about a main effect of being bullied or not? So this ignores the fact that there's males and females and just takes all the bullied people, lumps them together, compares their average hostility to the whole bunch of people who are not bullied. Where's that? Well, it's the bullied status row. Can we reject the null that adults are bullied and not bullied as kids are equally hostile as adults? Well, 0.042, that's less than 0.05. So yeah, there's some sort of like difference between people who were bullied or not as kids on their adult hostility. So what is it? Well, there's only 2 levels, so we don't have to get fancy here. We just need to look who was more hostile, who had the higher mean, bullied people who were bullied as kids versus people who are not bullied. And it's those who were bullied. So specifically, adults who were bullied as children, their mean was 9.45, are more hostile than those who were not bullied, 8.27. So it's not a big difference, right? 1.2 points. But they are, on average, when you're bullied as a kid, you're more hostile as an adult. It's real data. Okay, here's the fun one, right? This is are the effects of bullying different for males and females? That is the interaction effect. Where's that? It's on the line that is sex times bullied. Can we reject the null that the effects of bullying are the same for men and women? It's less than 0.05, right? So yeah, there's some sort of effect, meaning the effects of being bullied were different for men and women. That's what this means. Well, what? It was more, okay, who's more hostile, right? That's the question. That's the, what are you going to tell grandma? So we have to keep going and do simple effects tests. So because the interaction ANOVA is an omnibus test, it just tells you, yeah, the effects of one IV were different at the levels of the other. We have to do simple effects tests to determine exactly which means differ from each other. So there's some crap in here. Like, it's not that these means are wrong. I'm just trying to help eliminate like extra output that's on here. So you don't have to look at this, just to be clear. So I tell you, don't have to look at it. They're not wrong though. So simple effects tests for the interaction are obtained using something called syntax in SPSS in the univariate procedure. So I explained it on your SPSS output, but basically this whole time when you're clicking things in SPSS and clicking boxes and throwing variables in boxes, SPSS is actually a programming language, and it's writing this code in the background that's computer code. And syntax is just looking at the computer code, and you can actually alter it to get things that you can't get through the point and click menus. So we're going to add something, a compare statement specifically, and then you put the independent variable you want to compare within the levels of the other one. In the row that says e-means in this output. So when you pop in all your stuff in the SPSS window, you don't click OK at the end, you click paste, and that spits out the syntax, the computer language. And this is what that looks like. And so note this row that says e-means equals tables, it's fourth from the bottom, sex times bullied status, and it says compare bullied status. There we go. What that's going to do is within each level of the other variable that's left out, so sex, it's going to compare bullied status, those who were bullied or not. So it's going to compare among men, those who are bullied or not. Among women, those who are bullied or not. So this is along the lines, the way I had that plot earlier. So we're comparing bullied versus not separately for males and separately for females. It's two simple effects tests. At no point here are we comparing like bullied males to bullied females, right, or unbullied males to unbullied females. We're holding sex constant. We're saying within males, compare the average hostility of those who are bullied to the average hostility of those who are not. Same thing for females. So looking at the plot, we're going along the lines. Okay, we're going to hold sex constant, and we're going to compare for each sex those who are bullied or not to see if their hostility is different from each other. So there are two simple effects tests in this particular example, right? There's two levels of sex, and so we have to do an adjusted Bonferroni corrected alpha level of 0.05 divided by 2. Our new Bonferroni corrected alpha level is 0.025. So that's what we use to determine the statistical significance. It becomes our alpha for our simple effects tests. So let's do it. So here is our simple effects test. That compare statement gives you this univariate test thing here. Note that there's a row for male, our set of rows for male, a set of rows for female. That's it. What's being compared there? If you read, it kind of tells you. It's just that they can't write grammatically. So each F, so each set of tests here, right? One for male, one for female. Test the simple effects of bullied status within each level combination of the other effects shown. Well, there's only one other effect shown. It's whether you're male or female, right? So it is comparing bullied status within each sex is what they're trying to say. In an awful SPSS, it actually gets worse. You're gonna see some really bad grammar coming up in some of these procedures, but it does actually tell you that it's comparing people who are bullied or not, bullied status within each level of sex. So for each one, we use a Bonferroni corrected alpha level of 0.025. And again, how did we get this univariate table thing? Well, we added that compare bullied status. That's how we got it. So it will compare the one that you put in parentheses. There's all our means. Those are the things being compared, right? So let's do the first one. Bullied versus not bullied males. Do they differ in their adult hostility? Remember to use 0.025. There's your sig, and you get 0.002, good God, 0.006, definitely less than 0.025. So yeah, among males, there was a significant difference in their average adult hostility between those who were bullied or not. Okay, well, there's only two levels, they're bullied or not, so if it's significant, we just look at the means, right, to know who, like, were they more hostile if they're bullied or more hostile if they're not bullied. Boom, those are two means. Males, not bullied, yes, bullied. Those two things differ, 7.79 and 10.4. When were males more hostile? When they were, yes, bullied. So among males, those who were bullied were more hostile than those who were not bullied, I guess the full way of saying that. So in Scott language, males, bullied greater than not bullied in hostility, right? That's my shorthand. How about for women? So we use the same Bonferroni corrected alpha level. There's our sig. Is that less than 0.025? Hell no, it's not, right? You got an F that's 0. So among women, let's look at the means. First of all, there they are. 8.67 versus 8.6667. Very close, right? Almost the same number. Not shocking that's not significantly different, right? So among females, their hostility level was not different depending on whether they were bullied or not. They were equally hostile, I guess, regardless of whether they were bullied. So in Scott language, that's among females, bullied was equal to not bullied. So what's it all mean? This is the, what do you tell grandma? And this is that statement I always put that's like interpret the results and tell me what it means. Like, I still haven't figured out how to do this exactly after 20 years. I'm going to just put a picture of grandma on everyone's assignments, I think, or all the assignments moving forward. It's just, what do you tell grandma about like the effects of being bullied for men and women as a kid, okay? On how hostile they are. Well, overall, men who were bullied as children, their mean was 10.4. were more hostile as adults than men who are not bullied, 7.79. That's half the story though, right? What about women? Well, however, women were equally hostile regardless of whether they were bullied as children or not, okay? That sounds awful. But you get the idea. The bullying didn't have an effect on women's adult hostility, but it increased males' adult hostility. How about that? Grandma would get that. So being very visual, I like to look at the plots and to see if the plot of the means is consistent with what I get looking at the actual means numbers. So this is what SPSS gives you, and I added 0 on the y-axis, so it would be APA compliant. You get this under the plots menu, and I tell you on the instructions. But what you see is that among men, right, remember we did along the lines, among men, those who were bullied were more hostile than those who were not bullied. However, among females, they were equally hostile, or their hostility didn't change, whatever, regardless of whether they were bullied or not, okay? So that is consistent with what we saw in the means. So how about the measures of effect size? Excuse me. Remember, first thing is get that sum of squares total, and you got to hand calculate that. And basically everything is just the sum of squares for the effect divided by the sum of squares total. Ignore all that crap and just put those effects in your ANOVA table, sum them up to get the total line, sum it up to get the degrees of freedom line, and you will be fine. So your sum of squares total is equal to the sum of squares for the main effect of sex, plus the sum of squares for the main effect of bully, plus the interaction of sex and bullied, plus error will give you the correct total. There it is, 3,000, oh, nope, 3,248.087. So our eta squared for sex is 8.25. That's its sum of squares divided by that 3,000 blah, 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 blah. And you get a really teeny tiny number. Right? Remember, it wasn't significant, so it's 0.003, so 0.3% of the variance. It's teeny tiny. How about bullying? That was a significant main effect, right? So it's a little bit higher. It was 2.3% of variance accounted for. The interaction, also significant, and divide its sum of squares by that total, and you get 2.3% basically again. So, you know, the main effect of bullying accounted for 2.3%. The main effect, excuse me, the interaction of sex and bullying also accounted for its own unique 2.3%. Sex basically didn't account for anything. Nothing. So we do an ANOVA summary table. We copy all this stuff from the SPSS output. Make sure you note what you can cross out. That one line could be better over intercept. To your APA format table, there's Barf and Nessie. Everything goes right in there. Eta squared. Make sure to star your F's that are statistically significant, and you add up that total row. You gotta add up the sum of squares in DF on your own. Don't use the ones in SPSS. Even if it works this time, just get in the habit of doing it on your own, because it won't work moving forward. Everything comes from your output except eta squared, which I showed you how to calculate on the prior slide. So for your simple effects tests, remember they came in this weird sort of table that was out there with the really bad grammar. So these go in the text, so you write it up with the F thing, 1 and whatever degrees of freedom, 174. So for this example, for the effect of bullying within males, it's an F of 1 in 74 is equal to 7.76. P was less than 0.025. That's the corrected bond for any alpha, right? Eta squared 0.04. So that's 137, by the way, divided by the total on the prior page. So show you where everything comes from. Your simple effects, your eta squared is your sum of squares for the simple effects, divided by the sum of squares total on the prior table. So note it's 3248. It's not 3089. So it's not this error here, okay? All right. So for males, there's the formula. 137 does come from this table, but that 3248 came from the prior table, right? The table with all the effects in it. It was 0.04. And then for females, it's basically 0.